Hello there, and welcome to the Sleepy Now project, where tonight we'll drift together into the quiet world that exists beneath our feet. A world of hidden rivers and ancient waters that flow in darkness, carrying life itself through the secret spaces of the earth. Thank you for inviting this story into your quiet space tonight. In a world that rushes and demands, you've chosen to slow down, to listen, to let your mind wander through peaceful places. This gift of your time and attention is something I don't take lightly. Here, in this gentle hour, we can explore together without urgency, without the need to remember every detail. Let the words wash over you like water over stones, smoothing the rough edges of the day. Before we begin our journey into the Earth's hidden waters, I have a question for you. One you needn't answer aloud, but might hold gently in your mind. What are the softest places you've ever walked? Perhaps it was moss-covered forest floor after rain, or sand that had been kissed by retreating waves. Maybe it was fresh snow that yielded beneath your feet with barely a whisper, or garden soil, dark and rich, that seemed to breathe beneath your steps. Hold that memory of softness, that sensation of the earth receiving you gently. Tonight, we'll discover how that very softness connects to rivers you cannot see, to water that moves through darkness with the patience of centuries. If this story brings you peace, if it helps your thoughts settle like sediment in still water, perhaps you might let it ripple outward. Share it with someone who needs a moment of tranquility, someone whose mind could use a gentle journey away from the brightness and noise of waking life. Stories, like water, find their way to where they're needed most. Tonight, we're going to explore something both utterly familiar and deeply mysterious. Water. But not the water you see in rivers or lakes, not the rain that drums on rooftops or the ocean that stretches to meet the sky. No, tonight we're descending into the hidden water, the groundwater that moves through soil and stone like the Earth's own circulation system, like dreams moving through sleep, essential but unseen. Imagine, if you will, that beneath every landscape you've ever known, beneath mountains and meadows, beneath deserts and forests, beneath the very ground where you lie tonight, there exists another world. A world of water moving with impossible slowness through spaces so small they could barely admit a grain of sand. This is groundwater, the planet's most patient river system, its most secret lake, its quietest ocean. As we prepare to begin this journey together, let your body settle into wherever you're resting. Feel how you're held by bed or chair or floor, just as rainwater is held by soil. Notice how your weight distributes itself, how you sink slightly into softness, how the boundary between you and what supports you becomes less distinct. This is how water meets earth, not with sharp edges or clear borders, but with a gentle negotiation, a slow embrace. Let your breathing slow, and with each exhale, imagine you're releasing the day's accumulated tension, like water vapor rising from warm earth. With each inhale, draw in the quietness of deep places, the coolness of shadows beneath stones, the patience of water that has travelled for decades through darkness to reach a spring. Your mind, too, can begin its descent. Not a falling, but a gentle filtering downward, like water finding its way between root systems and rock layers. Let thoughts that no longer serve you slip away like water through sand, leaving only what's essential, your presence here, your breathing, the story that's about to unfold like an underground stream emerging into starlight. We're about to follow water on a journey that might take a single drop decades or even centuries to complete. We'll discover aquifers that hold water older than human civilization, springs that have been considered sacred for thousands of years, and the invisible architecture of stone and soil that makes life on the surface possible. But we'll explore all of this gently, with the same patience that water itself demonstrates as it seeps through limestone, as it collects in hidden pools, as it rises through capillary action to feed the roots of sleeping trees. Let us begin with the ground beneath us, this seemingly solid foundation that is, in truth, more like a sponge than stone. Even in places where the earth feels hard and unyielding, there exists a hidden architecture of spaces. Between grains of sand, within the tiny chambers of porous rock, Along the secret fractures in bedrock, water finds its home. Groundwater isn't an underground river in the way we might imagine, not usually a rushing torrent through caverns, though such things do exist in special places. Instead, picture it as water held in the embrace of Earth itself, occupying the spaces between things, the pauses between words, the silence between heartbeats. It moves, yes, but often so slowly that a turtle's pace would seem lightning quick by comparison. Think of a sponge resting in a shallow dish of water. The sponge doesn't contain tunnels or channels, yet water finds its way into every available space, held by nothing more than the attraction between water molecules and the sponge's material. The ground beneath us works in much the same way. What we call soil is really a congregation of particles, tiny fragments of rock, organic matter from plants and animals returning to Earth, spaces filled with air, and yes, water. Always water. In some places, the Earth is generous with its spaces. Sandy soils, for instance, with their relatively large particles, create roomy gaps where water can move with something approaching ease. Imagine pouring water onto a beach. How quickly it disappears, how readily the sand accepts this liquid visitor. This is permeability in action, the Earth's willingness to let water pass through. But in other places, the Earth is more cautious, more protective of its spaces. Clay soils, with their microscopic particles packed close together, admit water only reluctantly. Pour water onto clay, and it might pool on the surface, taking its time to negotiate entry, like a gentle conversation that cannot be rushed. This is low permeability, not a rejection of water, but a slower, more considered acceptance. And then there's porosity, not how easily water moves, but how much space exists to hold it. Some rocks, like sandstone, are riddled with tiny pockets, like a frozen foam that can hold surprising amounts of water. Others, like granite, offer few such spaces, their crystalline structure leaving little room for liquid guests. Yet even granite is not absolute in its solidity. Over millions of years, water finds the cracks, exploits the weaknesses, creates spaces where none existed before. This hidden architecture extends far deeper than we might imagine. While the soil layer might be only feet thick, the zone where groundwater resides can extend hundreds, even thousands of feet down. Down there, in the absolute darkness, water older than human memory waits in patient pools, moves through channels no eye has seen, follows gradients so gentle they're measured in inches per century. Consider what this means. At any given moment, there is more fresh water hidden beneath the Earth's surface than in all the rivers and lakes combined. While we marvel at the Amazon or the Nile, a vaster quantity of water moves in secret beneath our feet, supporting forests and grasslands, feeding springs and streams, waiting in reserve for the times when the rains fail to come. This groundwater doesn't simply sit still. It moves according to laws as old as physics itself, flowing from high pressure to low, from places of abundance to places of need. But unlike surface water, which might rush downhill in minutes or hours, groundwater moves with the patience of stone. A raindrop that falls today might not emerge from a spring for decades. Some water now rising in desert oases fell as rain when mammoths still walked the earth. The boundary between the dry earth and the water-saturated zone below is called the water table, though table suggests something flat and stable, which it rarely is. Instead, imagine an underground landscape that mirrors in slower motion and softer contours the hills and valleys above. The water table rises beneath hills, dips beneath valleys, coming closest to the surface where the earth's skin is thinnest, where springs are born and wetlands flourish. After heavy rains, the water table rises like a very slow tide, lifting the hidden sea within the earth. During droughts, it falls, retreating deeper, leaving roots to reach further for sustenance. This breathing of the earth, this rise and fall of hidden water, happens too slowly for us to perceive directly, yet every plant, every well, every spring bears witness to its movement. And what of the spaces themselves, these tiny chambers and corridors where water resides? In sand and gravel, the spaces are like tiny rooms between rounded particles, irregular but interconnected, creating a three-dimensional maze that water navigates by feel. In some limestone regions, water has carved actual channels and caves, creating underground rivers that run through cathedral-like spaces no human eye has seen. These karst landscapes, as geologists call them, are where groundwater most closely resembles our surface understanding of rivers and lakes. But most groundwater moves through spaces so small they challenge imagination. Picture the interior of a sandstone cliff. What looks solid to our eyes is actually millions of tiny spheres of ancient sand, cemented together but not completely, leaving a network of pores like a frozen constellation of bubbles. Through these spaces, some no wider than a human hair, water moves with infinite patience, pulled by gravity, pushed by pressure, drawn by the thirst of roots seeking sustenance. This is the secret beneath the soil, a world of water in motion so slow it seems like stillness, a reservoir so vast it dwarfs our surface waters, a system so essential that without it, most life on land would cease to exist. Every forest, every grassland, every oasis in the desert draws from this hidden wealth. Every well we dig, every spring we cherish, every cave we explore with wonder, all are windows into this secret world of groundwater, flowing in darkness, patient as stone, essential as breath. Let us follow a single drop of rain on its underground odyssey. A journey that begins in clouds and may not end for centuries. This is not a race but a meditation in motion, a story told at the pace of stone and soil rather than wind and weather. Our droplet forms high above the earth, where water vapour, lighter than air, has risen and cooled, condensing around a microscopic particle of dust, perhaps a grain of pollen carried aloft, or a crystal of salt born from evaporated sea spray. Up here in the cold heights, our drop joins with others, growing heavy enough to begin its fall. The descent through air takes only minutes, but already our droplet's fate is being decided. Will it fall on bare rock, on soil, on leaves? Will it land in a place prepared to receive it, or somewhere that will send it rushing away across the surface? These first moments of contact between rain and earth determine whether our drop will join the quick rivers of runoff, or begin the slow journey into groundwater. Let's say our drop falls on a forest floor, that soft place where decades of fallen leaves have created a spongy layer of duff and humus. The impact is gentle, not the sharp splash of water on stone, but a soft reception, like arriving home after a long journey. The droplet doesn't immediately sink. Instead, it beads on an oak leaf, joining with other drops until their combined weight causes them to roll off, falling again, this time onto moss. The moss receives the water like a mother accepting a child, drawing it in through countless tiny green fingers. But moss can only hold so much, and soon our droplet continues downward, now beginning to truly enter the earth. This is the process hydrologists call infiltration, though that clinical term hardly captures the intimacy of water meeting soil. In this first inch of descent, our droplet encounters a universe of obstacles and opportunities, grains of sand, each one a tiny mountain to navigate around, fragments of organic matter, the remains of leaves, insects, roots, creating a labyrinth of passages, clay particles flat as microscopic plates, forcing the water to flow in sheets between them, and everywhere, other water molecules, some that fell as rain yesterday, some that have been held in these shallow spaces for weeks. The movement isn't straight down. Gravity may insist on that direction, but the Earth has other ideas. Our droplet moves sideways as often as down, following the path of least resistance, drawn by the attraction of soil particles, pulled by the cohesion of other water molecules. It's like trying to navigate a crowd where everyone is holding hands. Progress is possible, but indirect. As our drop descends, the spaces become smaller but more regular. The chaotic architecture of the surface soil, constantly disturbed by roots and burrowing creatures, gives way to a more stable arrangement. Here, perhaps 6 inches down, our droplet might pause for days or weeks, held in the film of water that surrounds soil particles like an impossibly thin skin. This is the zone where most plants drink, where roots spread their fine hairs to sip from the earth's held moisture. But rain continues to fall above, and the pressure of new water pushes our droplet deeper. Now it leaves the realm of roots behind, descending into what scientists call the vadose zone, the unsaturated earth between surface and water table. Here, water moves in strange ways, clinging to the underside of particles, creeping along grain boundaries, occasionally forming tiny rivulets that race downward through larger pores before dispersing again into films and lenses of moisture. The journey through the vadose zone might take months. Our droplet moves like a mountain climber in reverse, always seeking handholds downward, sometimes moving laterally for great distances to find a path. In sandy soil, the descent might be relatively quick, days or weeks. In clay, our drop might take years to travel a few feet, held in the embrace of minerals that seem reluctant to let water pass. And then, at last, our droplet reaches the water table, that invisible boundary between the unsaturated earth above and the saturated zone below. This isn't a sharp line, but a transition, a place where the spaces between particles are no longer partially filled with air, but completely occupied by water. Our droplet joins this underground sea, becoming part of something vast and interconnected. But the journey doesn't end at the water table. Now our droplet is part of groundwater proper, moving according to different rules. No longer does it creep along particle surfaces, now it flows, albeit slowly, as part of a larger body of water. The movement is still measured in feet per year rather than miles per hour, but it is true flow, driven by gravity and pressure gradients. In the saturated zone, our droplet might travel through an aquifer, a layer of rock or sediment capable of holding and transmitting useful quantities of water. If it's lucky enough to be in a sand and gravel aquifer, it might move relatively quickly, perhaps a few feet per day. In a sandstone aquifer, the pace slows to feet per year. In some clay-rich formations, movement is so slow it's essentially storage. Water that fell as rain during the last ice age still waits in these deep, patient reservoirs. The path through an aquifer is rarely straight. A droplet might move horizontally for miles, following the tilt of rock layers laid down when dinosaurs walked the earth. It might descend deeper, pulled by gravity into confined aquifers trapped between impermeable layers. It might rise again, pushed by pressure from the weight of water behind it, seeking an exit back to the world of light. Throughout this journey, our droplet is never truly alone. It travels with companions that fell as rain in different centuries, mixing waters of different ages like a very slow conversation between generations. It might pick up minerals from the rocks it passes through, calcium from limestone, iron from sandstone, salts from ancient seabeds. These dissolved passengers will affect its taste if it ever emerges from a spring or well, giving different waters their distinctive flavours. Time passes differently down here in the dark. Seasons mean nothing. Years blur together. Our droplet might spend a human lifetime travelling the distance a surface stream covers in an hour. This is movement measured in geological time, patience exemplified in liquid form. And where does the journey end? Perhaps our droplet will emerge from a spring, blinking into sunlight after decades of darkness. Perhaps it will be drawn up through a well, returning to the surface world to water gardens or quench thirst. Perhaps it will seep into a stream bed, rejoining the quick waters of the surface. Or perhaps it will continue its deep journey for centuries more, part of the vast hidden circulation that makes life on the surface possible. This is the slow journey of a raindrop through the earth, a pilgrimage through darkness, a meditation in patience, a story told at the pace of stone. Every drop of groundwater has made this journey, is making this journey, will make this journey. And in their collective movement, slow as it is, lies the secret of how our planet stores water for the times when the rains fail, how it feeds rivers during droughts, how it keeps the earth alive during the long sleeps of winter and the fierce thirsts of summer. Chapter 3: The Aquifer's Architecture. Deep beneath the surface, beyond the reach of roots and the warmth of sun, lies an architecture more ancient than any human building, more complex than any city. This is the structure of aquifers, nature's own water storage system, built not with blueprints and cranes, but with time, pressure, and the patient work of water itself. Imagine, if you will, a library made of stone, where instead of books on shelves, water fills the spaces between grains of sand, occupies the tiny chambers within rock, flows through fractures no wider than a pencil line. Each type of rock, each geological formation, creates its own unique architecture for holding and transmitting water, its own way of writing the Earth's liquid history. Let us begin with sandstone, that most generous of aquifer rocks. Picture a cliff face of sandstone, its surface rough to the touch, its colour ranging from cream to deep red depending on the iron it contains. What you're seeing is millions upon millions of sand grains, each one a tiny piece of quartz or other mineral, weathered from ancient mountains and deposited by long-vanished rivers or seas. These grains were buried, compressed, cemented together by minerals precipitating from water, but never completely. Between the grains remained spaces, a three-dimensional network of pores. Hold a piece of sandstone and magnify it in your mind. You'd see a frozen foam of rock and air, where perhaps 20 or 30% of the volume is empty space. Now fill those spaces with water, and you have a sandstone aquifer. The water doesn't flow through tunnels or channels, but seeps through the interconnected pores, moving from one tiny chamber to the next like a very patient traveller navigating a vast city of microscopic rooms. The Nubian sandstone aquifer beneath the Sahara Desert is one such formation, holding water that fell as rain when the Sahara was green, tens of thousands of years ago. This fossil water, as hydrologists call it, waits in the darkness beneath one of Earth's driest places, a liquid memory of a climate long past. The sandstone holds this water like a vast underground sponge, releasing it slowly to oases and deep wells, drop by precious drop. Now consider limestone, that rock of ancient seas. Unlike sandstone's simple architecture of grains and pores, limestone offers a more complex story. Formed from the compressed remains of countless marine organisms, coral, shells, microscopic plankton, limestone begins as a relatively tight rock. But limestone has a secret. It dissolves in weak acid. Every raindrop carries a tiny amount of carbonic acid, formed when carbon dioxide from the air dissolves in water. This weak acid, no stronger than soda water, seems harmless enough. But given time, and geology always has time, this gentle acidity can dissolve limestone, creating spaces where none existed before. First, the water exploits existing cracks and joints, widening them grain by grain. Over millennia, these cracks become fissures, fissures become channels, channels become caves. In limestone country, aquifers can be wild, unpredictable things. Water might flow through tiny pores as in sandstone, but it might also race through underground rivers, complete with waterfalls and rapids that no human eye will see. The Edwards Aquifer in Texas is such a system, where water moves through a honeycomb of dissolved passages, some as small as pipelines, others as large as subway tunnels. Springs fed by such aquifers can be massive, discharging millions of gallons daily, the hidden architecture below revealed only by the volume of water emerging into daylight. But not all aquifers are created by nature's chemistry. Some are born of violence, fractures and faults created by the Earth's restless movements. Granite, that crystalline rock that seems so solid, so impermeable, can become an aquifer when cracked by tectonic forces. Water finds these fractures like a reader finding meaning between lines, flowing through spaces that are narrow but extensive, following the Earth's wounds for miles. In fractured rock aquifers, water moves like a secret message passed through a network of spies. It might travel quickly through major fractures, then pause where fractures narrow or end, seeking new paths, finding connections that map the Earth's ancient traumas. Wells drilled into such aquifers are exercises in hope. Miss the fractures by a few feet, and you find only dry, solid rock. Hit the fracture network and water flows. Between these water-bearing layers often lie the opposite, confining layers of clay or unfractured rock that water cannot penetrate, or penetrates so slowly it might as well be solid. These aquitards, as hydrogeologists call them, are like the floors and ceilings in our stone library, separating one story from another. They create confined aquifers, where water is trapped between impermeable layers like a pressed flower between pages of a book. Confined aquifers hold surprises, because the water within them is under pressure, the weight of all the rock and water above pressing down. It wants to rise. Drill a well into a confined aquifer, and water might rush upward, sometimes all the way to the surface or beyond, creating an artesian well. These flowing wells seemed magical to our ancestors, water rising from the earth without pumping, without effort, as if the earth itself were offering a gift. The Dakota sandstone stretching beneath the Great Plains is such a confined aquifer. Water that falls as rain on the Rocky Mountains' eastern slopes enters the sandstone and begins a journey eastward, trapped beneath layers of impermeable shale. Centuries later, this water might emerge from an artesian well in Kansas or Nebraska, having travelled hundreds of miles through darkness, pushed by the pressure of the mountains themselves. The architecture of aquifers isn't uniform, even within a single formation. Like a building with grand halls and narrow passages, an aquifer might be generous with water in one place, stingy in another. The rock might be more porous here, less fractured there. Clay lenses might interrupt the flow like doors closing off certain paths. Understanding an aquifer's architecture requires a kind of underground vision, an ability to see the invisible, to map the unmappable. Modern hydrologists use tools that would have seemed like magic to earlier generations. Electrical resistance surveys that detect water-bearing rocks, seismic waves that reveal layer after layer of the Earth's structure, chemical tracers that follow water's path like breadcrumbs through the darkness. But even with these tools, aquifers keep their secrets. Every well drilled is still partly an act of faith, every model of groundwater flow an approximation of a reality too complex to fully capture. And the architecture changes, slowly but continuously. Water dissolves minerals here, deposits them there. Earthquakes create new fractures, close old ones. Wells change the pressure dynamics, causing water to flow in new directions. The architecture of aquifers is not static like human buildings, but dynamic, responsive, alive in its own geological way. This, then, is where our groundwater lives, in architectures both simple and complex, in spaces measured in microns and miles, in formations young as yesterday's earthquake and old as the first rains that fell on newly cooled rock. Each aquifer has its own personality, its own way of receiving, holding, and releasing water. Each is a library of liquid history, an archive of ancient rains, a reservoir of patience in a world that often moves too fast. There is water beneath us older than the pyramids, older than the earliest human civilizations, older than the last ice age. This ancient groundwater, resting in deep aquifers, carries within it the memory of climates long vanished, of rains that fell when the world wore a different face. To drink such water is to taste time itself. Consider the Nubian sandstone aquifer system, that vast underground sea beneath the Sahara. The water held in its depths last saw daylight, when the Sahara was not a desert, but a green savanna dotted with lakes crossed by rivers, home to hippopotami and crocodiles. This was the Green Sahara period, ending some 5,000 years ago, when the Earth's orbital wobble shifted monsoon patterns and the rains gradually failed. But the water remained, sinking into the sandstone, held in the embrace of rock laid down when dinosaurs walked the Earth. Now it waits in darkness, this fossil water, untouched by the water cycle that refreshes most groundwater. It is, in essence, a liquid fossil, as removed from the present world as the bones of extinct creatures. Such ancient water exists in many places. Beneath the Great Artesian Basin of Australia lies water that fell as rain 2 million years ago. In parts of the Guarani Aquifer beneath South America, water has been in residence for tens of thousands of years. These are not active participants in the hydrological cycle, but prisoners of geology, held in underground vaults by overlying impermeable rocks, protected from the young waters of recent rains. How do we know the age of water hidden so deep? The water itself carries clues, written in the language of isotopes and dissolved gases. Just as tree rings tell the story of past seasons, the chemistry of groundwater reveals when it last touched air. Scientists look for radioactive isotopes, carbon-14, tritium, that decay at known rates. Young water still carries these markers of recent contact with the atmosphere. Ancient water has lost them to time's patient accounting. The water also carries chemical signatures of the climate under which it fell. The ratio of different oxygen isotopes reveals the temperature when the rain formed. Dissolved noble gases tell of the soil temperature when the water first entered the ground. These ancient waters are liquid time capsules, carrying information about climates that existed before human memory, before human existence. In Libya, wells drilled into the Nubian aquifer bring up water that is startlingly pure, free from the pollutants that mark modern precipitation. This water knew nothing of industry, of agriculture, of the 1,000 chemicals we've added to the atmosphere. It's water from a cleaner world, though whether that world was better or simply different is a question geology doesn't answer. The Great Artesian Basin's ancient water tells its own stories. When it emerges from springs or wells, it's often warm, heated by its long residence in the Earth's depths. It carries minerals dissolved from rocks it's touched over millennia, sometimes making it undrinkable, sometimes giving it properties that led indigenous peoples to consider certain springs sacred, healing. The famous mound springs of South Australia, where this ancient water emerges naturally, have been gathering places for thousands of years, oases of life in the arid outback. But ancient water is not renewable, not on any timescale meaningful to human life. When we pump fossil water from deep aquifers, we're mining it like coal or oil, a resource laid down in the deep past, irreplaceable in the present. The vast pivot irrigators that create green circles in deserts are often watered by rain that fell when mammoths walked the earth. When that water is gone, it's gone for good, or at least for tens of thousands of years. There's something profound about the slowness of deep groundwater, the way it opts out of the frenetic cycling of surface water. While a molecule of water in the ocean might evaporate, fall as rain, flow down a river, and return to the sea all within weeks, a molecule of deep groundwater might spend 1 million years in the same aquifer, held in the same pore space, touched only by other ancient waters. This slowness creates strange situations. In some deep aquifers, the water is older than the ocean water it originally came from. The seas have mixed and remixed countless times, while this water sat still in darkness. Continents have moved measurable distances. Mountain ranges have risen and worn away. Species have evolved and gone extinct, and still the water waits, patient as stone. The confined aquifers that hold ancient water are like underground museums, preserving not objects but the liquid essence of vanished climates. The water that falls as rain today on the Rocky Mountains might not emerge from springs in the Great Plains for centuries. The water beneath the Sahara might never rejoin the active water cycle, not until the slow dance of continents and climates brings rain back to what is now desert. Sometimes ancient water reveals itself in unexpected ways. Deep drilling for oil or minerals occasionally hits pockets of water, so old, so isolated, that they contain life forms equally ancient. Bacteria that have been separated from their surface cousins for millions of years, evolving in darkness, living on chemicals rather than sunlight. These discoveries remind us that even the oldest, deepest waters are not sterile, but can harbour life as patient as the water itself. The age of groundwater matters for practical reasons too. Young groundwater, recently recharged, responds quickly to contamination, but also cleans itself relatively quickly as fresh water flushes through. Ancient groundwater, once contaminated, might stay that way for geological ages. It's one reason why pollution of deep aquifers is so serious. There's no waiting for the system to cleanse itself, not on any timescale we can afford to consider. As we draw more heavily on groundwater resources worldwide, we increasingly tap these ancient reserves. The Ogallala Aquifer beneath the American Great Plains, though not as old as fossil water, contains water that fell as rain centuries ago. We're using it far faster than nature can replace it, spending our liquid inheritance like profligates burning through a trust fund. Yet there's also wonder in this ancient water, a kind of time travel in liquid form. Every glass drawn from a deep well might contain water older than any human artifact, older than agriculture, older than language. It connects us to deep time in a way few things can. We drink the same water that fell on landscapes we can barely imagine. Water that has been waiting in darkness for our species to evolve, to develop the technology to reach it, to need it. This ancient water reminds us that the Earth operates on timescales that dwarf human experience. What seems permanent to us, the desert, the locations of rivers, the climate itself, are all temporary when viewed from the perspective of deep groundwater. The water knows. It remembers when the Sahara was green, when the Great Plains were beneath a sea, when the continents themselves wore different faces. In the darkness of deep aquifers, time moves differently. Water that will not see sunlight for another 1,000 years mingles with water that has been waiting since before humans learned to speak. This is patience exemplified, time made liquid, the Earth's longest thoughts expressed in H2O. To contemplate ancient groundwater is to glimpse geological time, to feel our own brevity, to understand that we are borrowing from the past in ways we're only beginning to comprehend. Where groundwater returns to the light, magic happens. Springs, those places where the underground rivers reveal themselves, have captivated humanity since our species first walked upright. They are birthplaces of rivers, oases in deserts, sacred sites where the earth offers up its hidden wealth. Each spring tells a story of pressure and geology, of water finding its way back to the world above. Picture a hillside where water seeps from the earth, not dramatically but persistently, a weeping of the land that never ceases. The ground here is different, softer, darker, alive with mosses and ferns that thrive in perpetual moisture. The air carries a coolness even on hot days, a mineral scent that speaks of deep places. This is a spring at its most gentle, where groundwater emerges not through force, but through patient persistence. Springs are born where geology and hydrology conspire to bring hidden water to the surface. Perhaps an impermeable layer of clay forces water to flow laterally until it finds the hillside's face. Perhaps a fault has created a pathway for deep water to rise. Perhaps the water table simply intersects the land surface in a valley or depression. Each spring has its own genesis story written in rock and water. The personality of a spring reflects the aquifer that feeds it. Springs fed by shallow local groundwater might vary with the seasons, flowing strongly in wet times, reducing to a trickle or failing entirely in drought. These are young waters, recently fallen as rain, quick to respond to the weather's moods. Their temperature varies with the seasons, their flow mirrors recent precipitation. But springs fed by deep aquifers tell different stories. They flow steadily through drought and flood. Their output as reliable as the aquifer is vast. Their temperature remains constant year-round, a thermal signature of their underground journey. In winter, such springs seem warm, steaming in the cold air. In summer, they offer cool refuge. They are windows into the stable world below, where seasons barely penetrate. Some springs announce themselves grandly. Florida's springs, fed by the vast Floridan aquifer flowing through limestone, discharge millions of gallons daily through underwater caves. The water emerges with such clarity that looking into a spring pool is like looking through air. You can see fish swimming at depths that seem impossible. Every grain of sand on the bottom visible through water so pure it seems to vanish. These first magnitude springs, as hydrologists classify them, are really rivers being born fully formed. Silver springs, Wakula springs, Rainbow springs. Each discharges enough water to float boats, to create ecosystems, to have supported human settlements for thousands of years. The water emerges from cave mouths large enough to swallow buildings, having travelled through the limestone's dissolved architecture for decades. At the other extreme are the small seeps, the weeping rocks, the places where water emerges drop by drop. These might support only a small patch of green in otherwise dry land, but to desert travellers, to wildlife, To the plants that cluster around them, they are no less miraculous than their grander cousins. A spring need not be large to be significant. Hot springs occupy their own category of wonder. Here, groundwater has descended deep enough to be heated by the Earth's own warmth, then found a quick path back to the surface. The water emerges carrying dissolved minerals from depths no surface water reaches: sulfur, silica, calcium carbonate. These minerals often precipitate as the water cools, building terraces of travertine, painting rocks in impossible colours, creating landscapes that seem more artwork than geology. Yellowstone's hot springs, Pamukkale's white terraces in Turkey, the sacred hot springs of Japan, each represents groundwater's journey to the Earth's heated interior and back. The water tells its story in steam and stone, in colours created by heat, loving bacteria, in the slow construction of mineral architecture. Some hot springs have been flowing for millions of years, building mountains one molecule at a time. Springs have always been more than mere water sources to humanity. They are places where the mysterious underground reveals itself, where water appears as if by magic. Small wonder that so many springs have been considered sacred. The oracle at Delphi spoke from above a spring. Rome's springs were guarded by nymphs. Celtic peoples threw offerings into spring pools, trusting the water to carry their prayers to the underworld. The Ganges emerges from a spring at Gangotri, high in the Himalayas, a place of pilgrimage for millions. The spring at Lourdes draws those seeking healing. The cenotes of the Yucatan, those spring-fed pools and collapsed limestone, were sacred to the Maya, portals to the underworld. Even in our scientific age, springs retain their aura of mystery, their suggestion of hidden depths revealing themselves. Springs create ecosystems unlike any others. The constant water, stable temperature, and unique chemistry support specialized communities of life. Some species exist only in single spring systems, having evolved in isolation for millennia. The devil's hole pupfish lives only in one deep spring pool in Nevada, a species confined to a habitat you could cover with a small tarp, yet persisting there since the last ice age. Spring-fed streams support fish populations through droughts that dry up surface-fed waters. Watercress and other spring specialists thrive in the mineral-rich flow. In deserts, springs support palm oases, creating vertical forests in landscapes otherwise dominated by horizontal sprawl. The reliability of springs has made them centres of biodiversity, arcs preserving life through climatic changes. Human history is inseparable from springs. Our settlements clustered around reliable water sources. Trade routes connected spring to spring across deserts. The names of countless towns include springs: Alice Springs, Palm Springs, Hot Springs, Silver Springs. Before we learned to drill wells, springs were groundwater's primary gift to surface life. But springs are also vulnerable, early warning systems for what we're doing to groundwater. When springs that have flowed for millennia begin to fail, when their flow diminishes or their water quality changes, they're telling us about invisible changes below. A spring is groundwater's report card, revealing the health of hidden aquifers. Some springs have already fallen silent, victims of overpumping from the aquifers that fed them. Others flow with diminished vigour, their reduced flow telling of water tables dropping, of aquifers under stress. Each failed spring is a broken connection between the upper and lower worlds, a conversation ended, a gift withdrawn. Yet where springs still flow, they remain places of wonder. To cup spring water in your hands is to hold the end result of a journey that might have taken centuries. This water has known the darkness of the deep earth, has moved through spaces no light touches, has dissolved and deposited minerals in an underground chemistry we're only beginning to understand. Now it emerges, called back to the surface by geology and gravity, ready to begin again the cycle that connects cloud to sea to cloud. Watch a spring closely, and you might see it pulse, the flow varying subtly with pressures transmitted through the aquifer from distant rains. Some springs respond to tides, even far inland. The moon's pull felt through the Earth's elastic response. Others vary with barometric pressure, breathing with the weather. Each spring is alive in its way, a pulse point where we can feel the Earth's liquid heartbeat. This is the quiet emergence of groundwater, through springs grand and humble, hot and cold, constant and variable. Each is a gift from the darkness below, a place where patient water returns to impatient air, where the hidden world reveals one of its many faces. In their flow we read stories of rain that fell when the world was young, of water's slow journey through stone, of the generosity of an earth that stores water in darkness and releases it into light, sustaining life with the patience of ages. Deep beneath us, in the perpetual midnight of groundwater, life persists, not the familiar life of the surface. No plants painting food from sunlight, no animals browsing or hunting in the green world above. Instead, a different kind of existence thrives in the darkness, microscopic, patient, as alien to our daily experience as creatures from another planet, yet essential to the health of the water we drink and the cycles that sustain our world. Imagine descending through the earth into an aquifer, shrinking as you go until you could swim through the pore spaces between sand grains. Here, in spaces barely wide enough to admit a few bacteria lined up side by side, entire ecosystems flourish. The surfaces of sand grains are not barren but coated with biofilms, communities of microorganisms living in their own secreted structures, like microscopic cities built of slime and purpose. These bacteria, archaea, and other microorganisms have adapted to life without light, without the oxygen that most surface life requires, without the temperature variations that mark days and seasons above. They are the deep Earth's quiet alchemists, transforming minerals and molecules in ways that profoundly affect groundwater chemistry, and, ultimately, the water that emerges from our wells and springs. Some of these organisms breathe iron instead of oxygen, converting dissolved iron from one form to another, painting aquifers in shades of rust and red. Others breathe sulfur, producing the rotten egg smell that sometimes accompanies deep groundwater. Still others work with nitrogen, converting nitrates that might otherwise contaminate drinking water into harmless nitrogen gas that bubbles away. Each type of microorganism has found its niche in the underground economy of elements. The diversity of this hidden life astounds scientists who study it. In a single drop of groundwater might swim hundreds of species, most unknown to science, many impossible to grow in laboratories. They've evolved in isolation for millions of years, adapting to specific conditions of chemistry and temperature, pressure and flow. Some can survive on the tiniest amounts of organic carbon, scraping a living from molecules that seep down from the root zone far above. Others have learned to live entirely on inorganic chemicals, manufacturing their food from rock and water alone. These chemosynthetic organisms are Earth's most independent life forms, needing neither sunlight nor the products of photosynthesis. They create organic molecules from carbon dioxide just as plants do, but using chemical energy instead of light. In the deepest aquifers, kilometers below the surface, such organisms might be the only life, persisting in hot darkness since their ancestors were first buried by accumulating sediments. The pace of life in groundwater makes even geological processes seem hurried. Some deep subsurface bacteria divide only once per century, their metabolism slowed to the barest whisper of activity. They exist at the very edge of what we might consider living, yet they persist, waiting through the centuries for the rare meal of organic carbon or the perfect chemical conditions for growth. This is patience taken to an extreme that challenges our definition of life itself. Yet this slow life shapes the underground world in profound ways. Bacteria can clog pore spaces with their biofilms, redirecting groundwater flow. They can dissolve minerals, opening new passages, or precipitate minerals, sealing paths that water once followed. They transform the chemistry of passing water, removing some substances, adding others, acting as a vast, slow filter that processes groundwater over decades and centuries. In some aquifers, bacteria have created their own monuments. Iron bacteria, oxidizing dissolved iron for energy, precipitate rust-coloured deposits that can build up over millennia into thick layers. Sulfur bacteria create deposits of elemental sulfur, painting cave walls yellow. Some bacteria even precipitate tiny magnets. crystals of magnetite that orient themselves to Earth's magnetic field, helping the bacteria navigate in the darkness. The discovery of extensive life in deep aquifers has revolutionized our understanding of Earth's biosphere. We now know that the mass of subsurface microorganisms might equal or exceed all surface life. Forests and grasslands, with all their visible glory, might be matched by the invisible forests of microbes living in groundwater and deep rock. This hidden biosphere processes elements, stores carbon, and affects global chemistry in ways we're only beginning to appreciate. Some of the most remarkable groundwater organisms live in caves, where underground streams have carved passages large enough for exploration. Here, in the deeper reaches where no light penetrates, live creatures that seem designed by an artist exploring the theme of absence. Cave fish without eyes, their bodies pale as paper, amphipods like ghostly shrimp, salamanders stretched thin and white, their skin translucent enough to show internal organs. These cave-adapted creatures, evolved in isolation, demonstrate life's ability to adapt to the most extreme environments. Without light, eyes become useless appendages, so evolution has erased them. Without sun to fade pigments, colour serves no purpose, so creatures become translucent ghosts. With food scarce, metabolism slow to a crawl, some cave salamanders can go years without eating, waiting in the darkness for the rare cricket or worm to wash into their domain. The food webs in these dark ecosystems are sparse but intricate. At the base might be bacteria feeding on minerals or organic matter seeping from above. Tiny invertebrates graze on the bacterial films, larger invertebrates hunt the smaller ones. The occasional salamander or fish crowns this simple pyramid. Energy is so scarce that every calorie counts. Every meal might be separated by months of fasting. Yet even in this scarcity, there is strange abundance. Some caves harbour thousands of bats whose guano feeds entire ecosystems. The bats bridge the sunlit and dark worlds, hunting insects above, depositing nutrients below. In such caves, the rain of guano supports beetles, flies, and other invertebrates in numbers that seem impossible in the darkness. Even here, though, life has adapted to the specific conditions: guano beetles that can process what most creatures would find toxic, flies that complete their entire life cycle in the ammonia-rich environment beneath bat roosts. Groundwater creatures often show remarkable adaptations to their liquid world. Some have elongated bodies and limbs, the better to navigate narrow spaces. Many have enhanced chemical senses, elaborate antennae or sensitive skin that can detect the faintest traces of food or mates in the darkness. Some cavefish have evolved lateral line systems so sensitive they can detect the pressure waves from a small crustacean moving inches away, hunting by remote sensing in the absolute darkness. The isolation of groundwater habitats has created natural laboratories for evolution. Each cave system, each aquifer, might harbour species found nowhere else on Earth. The Edwards Aquifer of Texas alone hosts dozens of endemic species, creatures that exist only in that one underground water system. When we pump such aquifers dry or contaminate them, we risk erasing species that have persisted for millions of years, that carry in their DNA unique solutions to the challenge of existence. This hidden life also provides services we rarely consider. The microorganisms in aquifers help purify water, breaking down contaminants, transforming harmful compounds into harmless ones. They're nature's water treatment plant, operating continuously in the darkness, requiring no power but chemical gradients, no maintenance but the flow of water and time. When we overwhelm these systems with pollutants, we damage not just water quality but the living filters that have protected groundwater for eons. Research into deep subsurface life has implications beyond Earth. If life can persist kilometers deep in Earth's crust, living on chemicals and heat alone, might similar life exist in the subsurface of Mars or in the ocean beneath Europa's ice? The organisms in our aquifers might be analogues for the most common form of life in the universe, not the surface dwellers dependent on starlight, but the deep dwellers making their living from planetary chemistry. As we sit in the comfort of the surface world, it's humbling to realise that beneath us stretches another realm of life, vast and ancient, operating by different rules. Every glass of groundwater we drink has passed through this hidden ecosystem, has been touched by organisms we'll never see, has been processed by metabolisms we're only beginning to understand. The water carries within it the signatures of this dark life, changed chemistry, filtered contaminants, the subtle alterations that come from sharing space with Earth's most patient organisms. This is life in the darkness of groundwater, microscopic and resilient, ancient and essential, as far from our daily experience as the deep ocean, yet as close as the nearest well. It reminds us that life finds ways to persist in the most unlikely places, that even the seemingly sterile darkness of deep aquifers teems with quiet activity, that water and life are inextricably linked in ways both visible and hidden. In recognizing this dark life, we acknowledge that the underground waters are not mere resources but ecosystems, not just chemistry but biology, not just storage but process, alive in ways that expand our understanding of what it means to be alive. Long before we understood aquifers or water tables, before we could speak of porosity or permeability, humans knew groundwater. We knew it in the coolness of cave springs where our ancestors sheltered. We knew it in the places where water seeped from hillsides, creating ribbons of green in dry landscapes. We knew it in the mystery of wells, those vertical doors to the underworld that yielded life-giving water to those who knew where to dig. The history of human civilization is inseparable from groundwater. The earliest permanent settlements clustered around springs and seeps, those reliable water sources that flowed even when rivers ran low. Jericho, one of the world's oldest continuously inhabited cities, was built around a spring that still flows today, 10,000 years of human history sustained by the patient upwelling of ancient water. In Persia, 5,000 years ago, humans began one of the most audacious groundwater projects ever attempted, the qanats. These underground channels, hand-dug by specialized workers called muqanis, transported groundwater from mountain aquifers to and valleys dozens of miles away. The muqanis worked in darkness, digging horizontal tunnels that followed the water table with a precision that astounds modern engineers. They navigated by oil lamp and instinct, creating underground aqueducts that some still flow today. A qanat is more than engineering. It's a negotiation with the hidden world. The tunnel must slope gently enough to prevent erosion, but steeply enough to keep water flowing. It must tap the aquifer without draining it, transport water without losing it to evaporation. Vertical shafts every 100 feet or so provided air and access, creating lines of wells that march across the landscape like ancient punctuation marks. From above, a qanat looks like a string of periods leading from mountain to town, but below ground it's a river running in darkness, defying the desert. The Romans, those master engineers of water, understood groundwater too. While their towering aqueducts capture our imagination, much of Rome's water came from springs in the surrounding hills. They built elaborate structures to capture and protect these springs, understanding that the reliability of groundwater made it precious beyond measure. Roman texts describe methods for finding groundwater, watching for vegetation changes, observing morning mists, even tasting the earth for subtle hints of moisture below. In medieval Europe, the art of well digging became almost mystical. Water dowsers walked the land with forked hazel branches, claiming to feel the pull of underground water. Whether through unconscious observation of landscape clues or mere chance, they often succeeded in locating productive wells. The dowser's art spread worldwide, adapting to local conditions and beliefs, but always centered on the same mystery: how to find the invisible water that flowed beneath our feet. Wells themselves became community centers, gathering places where water and news flowed with equal importance. The village well was often the heart of settlement life, a place of daily pilgrimage for water carriers, a social hub where information was exchanged, a symbolic center where the underground world met the surface. In many cultures, wells were considered sacred, portals to the underworld that required respect and proper ritual. The step wells of India represent perhaps the most elaborate architectural response to groundwater. These inverted temples, carved deep into the earth, celebrated the descent to water. In Gujarat and Rajasthan, where the water table could drop dramatically between monsoons, stepwells like the Rani Ki Vav provided not just access to water, but cool refuge from the desert heat. Carved with the same elaboration as above-ground temples, they honoured water as divine, the journey to reach it a form of pilgrimage. Different cultures developed different relationships with groundwater, each reflecting local geology and climate. In the American Southwest, ancestral Puebloan peoples built their communities around springs, understanding the landscape's hydrology with an intimacy born of necessity. They knew which springs were permanent, which seasonal, which would flow in drought years. This knowledge, passed down through generations, meant survival in a land where water scarcity was the rule, not the exception. Aboriginal Australians navigated their continent by memorising the locations of water sources, many of them springs and soaks invisible to untrained eyes. Their songlines, oral maps passed down through millennia, encoded the locations of reliable water along with cultural knowledge. A series of hills might be remembered as the sleeping body of an ancestor, with the spring at a specific location marking where the ancestor's tears fell. Story and survival intertwined, with groundwater at the heart of both. The industrial age brought new ways to access groundwater. The cable tool drillers of the 19th century could reach depths impossible by hand digging. The rhythmic thud of their drilling rigs became the sound of progress, each blow driving deeper into the Earth's hidden reservoirs. When rotary drilling arrived in the 20th century, even deeper aquifers came within reach. Suddenly, humans could tap fossil water laid down before our species existed. This technological leap had profound consequences. The Great Plains of North America, once thought suitable only for cattle grazing, became one of the world's great grain-producing regions thanks to irrigation from the Ogallala Aquifer. Centre-pivot irrigation systems drawing ancient water through high-capacity wells created green circles visible from space. The desert bloomed, but at a cost measured in dropping water tables and a resource mined rather than sustainably used. Cities too have always depended on groundwater more than most residents realise. Before modern water treatment plants, urban wells and springs provided most municipal water. London's growth was supported by numerous wells tapping the chalk aquifer beneath the city. Paris had its own network of springs and wells. Even today, many cities depend partially or entirely on groundwater. San Antonio draws from the Edwards Aquifer. Memphis taps ancient sand aquifers beneath the Mississippi River Valley. Perth relies on the Nangara Mound. But our relationship with groundwater has often been troubled by what we couldn't see. Industries sited their factories atop aquifers, assuming the earth would absorb whatever waste they produced. Dry cleaners, gas stations, chemical plants all contributed cocktails of contaminants that seeped through soil into groundwater. By the time we understood the connections, plumes of contamination were already spreading through aquifers, invisible and persistent. The discovery of widespread groundwater contamination in the late 20th century changed our relationship with the hidden water. Places like Love Canal and Woburn became cautionary tales of how human activities at the surface could poison water deep below. The realization that chemicals spilled today might contaminate wells for generations forced a new awareness of groundwater's vulnerability and value. Traditional knowledge about groundwater, long dismissed by modern science, has proven remarkably accurate. Indigenous peoples' understanding of spring behaviour, acquired through millennia of observation, often matches or exceeds scientific surveys. The Kannat builders' intuitive grasp of groundwater flow anticipated principles hydrogeologists would later quantify. The dowsers' attention to subtle landscape clues, vegetation changes, soil differences, topographic hints, identified the same features modern surveys seek with sophisticated instruments. Today we stand at a crossroads in our relationship with groundwater. We have the technology to map aquifers in unprecedented detail, to model their behaviour with powerful computers, to drill wells that can extract vast quantities of water, but we also face dropping water tables worldwide, contamination that will persist for generations, and the challenge of sharing finite groundwater resources among growing populations. Some cities are pioneering new approaches, treating aquifers not just as sources but as storage systems, banking excess surface water underground during wet years for withdrawal during droughts. Others are learning from traditional systems, building modern versions of qanuts and infiltration galleries that work with natural processes rather than against them. The most forward-thinking are beginning to manage groundwater and surface water as the connected system they've always been. Our future with groundwater will require combining ancient wisdom with modern technology, traditional knowledge with scientific understanding. We need the Mercani's patient attention to underground flow and the hydrogeologist's mathematical models. We need the sacred springs reverence and the treatment plant's chemistry. We need to remember that groundwater is not just a resource, but a relationship between rain and rock, between past and present, between human communities and the hidden waters that have always sustained them. This is the human thread in groundwater's story. 10,000 years of finding, using, celebrating, and too often abusing the water beneath our feet. From the first spring that drew our ancestors to settle, to the deep wells that water modern cities, we have been shaped by groundwater as surely as water shapes stone. Our challenge now is to shape our relationship with groundwater as thoughtfully as those ancient engineers who dug qanuts through mountains, understanding that what flows in darkness supports all that lives in light. How do you map the invisible? How do you measure what moves in darkness? Quantify what flows through spaces too small to see? Modern hydrogeology is the art of listening to the earth, of reading the subtle signals that reveal the hidden architecture of water. With tools both simple and sophisticated, we've learned to peer through rock and soil, to trace the paths of underground water, to understand the liquid secrets the earth keeps. It begins, often, with observation, the same skill our ancestors used, refined by centuries of scientific understanding. A hydrogeologist walking the land reads it like a book written in the languages of geology and water. That line of willows in an otherwise dry valley whispers of water near the surface. The way a hill slope changes from brown grass to green suggests a spring line where groundwater emerges. Even the types of rocks exposed in road cuts and stream banks tell stories about what lies beneath and how water might move through it. But observation alone can only tell us so much. To truly understand groundwater, we must listen more carefully, must find ways to sense what our eyes cannot see. One of the simplest methods is also one of the oldest, the test well. Drilling or digging into the earth, we create a window into the underground, a place where hidden water can reveal itself. The depth to water, the rate at which a well refills after pumping, the way water levels change with seasons, all provide clues about the aquifer's nature. Modern wells are more than simple holes in the ground. They're equipped with sensors that continuously monitor water levels, temperature and chemistry. Data loggers record measurements every few minutes, creating detailed chronicles of how groundwater responds to rainfall, pumping, and the 1,000 other influences that affect underground water. A network of such monitoring wells becomes like a medical monitoring system for an aquifer, tracking its vital signs, alerting us to changes that might signal problems. To see deeper and wider than wells alone allow, we've learned to use the earth itself as a messenger. Electrical resistivity surveys send currents through the ground, measuring how easily electricity flows through different materials. Water-saturated sand conducts electricity differently than dry sand, clay differently than gravel. By mapping these differences, geophysicists can create three-dimensional images of the underground, showing where water likely flows and where it's blocked. Seismic surveys, adapted from oil exploration, use sound waves to probe the earth. A controlled impact at the surface, sometimes as simple as a hammer blow, sometimes a specialized vibrating truck, sends waves through the ground. Different rock layers reflect these waves differently, and water-filled spaces have their own acoustic signature. Geophones arranged across the surface listen for the echoes, and powerful computers transform these whispers from below into images of underground structure. Even more subtle are the methods that detect the tiny changes in Earth's gravitational and magnetic fields, caused by variations in underground density and composition. Where porous, water-filled sandstone replaces dense granite, gravity decreases minutely. Where ancient river channels filled with gravel cut through surrounding clay, magnetic fields shift slightly. Instruments sensitive enough to detect these whispers of difference help map the architecture that controls groundwater flow. But perhaps the most elegant methods of listening to groundwater involve the water itself as a messenger. Tracers, harmless dyes or chemicals added to water at one location, can be tracked as they move through an aquifer. A fluorescent dye poured into a sinking stream might emerge weeks later from springs miles away, revealing connections invisible from the surface. The time it takes, the concentration when it arrives, the path it follows, all tell stories about the underground plumbing. Natural tracers are even more revealing. Every water carries chemical signatures of where it's been, what rocks it's touched, how long it's been underground. Oxygen isotopes reveal the temperature when rain fell. Tritium from nuclear testing in the 1950s and 60s marks water that's been underground for specific decades. Noble gases dissolved in groundwater remember the temperature of the soil when the water first ascended. Like forensic scientists, hydrogeochemists read these clues to reconstruct water's history. Temperature itself is a powerful tool for understanding groundwater. Cold water sinking into a losing stream creates a plume of coolness that can be tracked through an aquifer. Springs carry the thermal signature of their source aquifers. Even the tiny temperature differences between day and night at the surface propagate into the ground, creating waves of warmth and cooling that reveal how water moves through the shallow subsurface. Modern technology has given us eyes that see beyond human limitations. Satellite imagery reveals subtle differences in vegetation that mark shallow groundwater. Areas that stay green longer during dry periods often overlie zones where roots can reach groundwater. From space, we can map the invisible by reading the biological responses to hidden water. Satellite radar can detect ground surface changes of millimeters, revealing where groundwater pumping causes land subsidence. Parts of California's Central Valley have sunk dozens of feet due to groundwater extraction, and satellites track this slow-motion collapse with precision that would have seemed magical to earlier generations. The Earth's surface becomes a membrane that reveals pressure changes in the water below. Computer models have revolutionized our ability to understand and predict groundwater behavior. Fed with data from all these listening methods, models simulate the three-dimensional flow of water through complex geological structures. They can predict how contamination might spread, where wells should be placed, how aquifers might respond to climate change. Like weather forecasting, groundwater modeling combines physics, mathematics, and massive computational power to peer into the future. But all this technology hasn't replaced the need for human intuition and experience. The best hydrogeologists combine high-tech tools with old-fashioned landscape reading, scientific analysis with something approaching art. They develop a feel for how water moves through specific types of geology, an intuition for where productive aquifers might lie. Like the water dowsers of old, they often sense what the instruments later confirm. Indigenous knowledge holders remind us that there are other ways of listening to the Earth. Traditional knowledge, accumulated over millennia of observation, often identifies groundwater patterns that scientific surveys later verify. Aboriginal Australians speak of water serpents whose underground paths mark the locations of springs and groundwater. These mythological mappings encode accurate hydrogeological information in forms that persist across generations. The integration of different ways of knowing, scientific and traditional, quantitative and intuitive, technological and experiential, offers the richest understanding of groundwater. When native plant experts, local farmers, indigenous elders, and university-trained hydrogeologists share their different perspectives on the same landscape, a fuller picture emerges than any one approach could provide. As our tools for listening to the Earth become more sophisticated, we're discovering that groundwater systems are more complex, more interconnected, more responsive to human influence than we once believed. We're learning that aquifers we thought were separate communicate through subtle fractures. We're finding that water we believed moves slowly can sometimes race through unknown channels. We're discovering deep waters we never knew existed, and connections between surface and groundwater we never suspected. This growing ability to hear what the Earth tells us about its hidden water comes with responsibility. The more clearly we can listen, the more clearly we hear warnings about over-extraction, contamination, and the fragility of systems we've long taken for granted. The instruments that reveal groundwater's secrets also document its distress, dropping water tables, spreading contamination plumes, the slow-motion crisis of aquifer depletion. Yet our improving ability to listen also reveals possibilities. We're finding aquifers where none were thought to exist, understanding recharge processes that can be enhanced, discovering natural treatment systems that can be protected and utilised. Each new method of listening, each refinement of our underground ears, brings both sobering knowledge and hope. Learning to listen to the earth is an ongoing process, a conversation that deepens with time and attention. Every well drilled, every spring sampled, every geophysical survey completed adds another note to our understanding of the underground symphony. And like any deep listening, it changes not just what we know, but who we are, transforming us from users of an invisible resource to partners in a conversation with the living earth, participants in the slow flow of water through stone, listeners to the patient stories that water tells as it moves through darkness toward light. Picture a well that has flowed for generations, its cool water drawn up by rope and bucket, then by mechanical pump, a reliable source that seemed as permanent as the earth itself. One summer, the pump begins to labour. The water level, once just 20 feet down, has dropped to 50, then 100. Finally, only air emerges. The well has gone dry. This scene, repeated countless times around the world, tells a story of drawdown and depletion, of humanity learning harsh lessons about the limits of even the vastest aquifers. Groundwater seems infinite when you cannot see its boundaries. Hidden beneath the earth, measured in cubic miles, moving so slowly that human-caused changes take decades to manifest, aquifers give an illusion of inexhaustibility. But illusion it is. We are conducting an unplanned experiment on a global scale, withdrawing water accumulated over millennia in mere decades, mining our liquid inheritance like a resource that need never be replenished. The mathematics of groundwater balance are simple in principle, complex in practice. Water enters aquifers through recharge, rain and snow soaking into the ground, streams losing water to permeable beds, irrigation water percolating below the root zone. Water leaves through natural discharge to springs and streams, through evapotranspiration where roots reach groundwater, and increasingly through human extraction. When withdrawal exceeds recharge, water tables fall. It's accounting written in water rather than ink. But this accounting happens underground, invisible to most who depend on it. A forest may show drought stress within weeks of rainfall deficits. A reservoir's dropping level is obvious to any observer, but an aquifer being depleted. The signs are subtle at first, wells needing to be deepened, springs flowing less vigorously, wet meadows gradually drying. By the time the symptoms are undeniable, the patient is seriously ill. The Ogallala Aquifer beneath the American Great Plains exemplifies our challenge. This underground sea, containing enough water to cover the entire United States to a depth of 18 inches, accumulated over millions of years. In some places, we've drawn it down by more than half in less than a century. The arithmetic is stark. Water that fell as rain when mammoths roamed now pivots through centre-pivot irrigators, growing corn and cotton in what would otherwise be semi-arid prairie. When it's gone, and at current rates some areas have only decades left, it's gone for timescales that make human planning irrelevant. Yet depletion is only one face of groundwater's fragility. Contamination presents an equally serious, often more intractable challenge. Surface water pollution, visible and obvious, often triggered the environmental movements that led to cleaner rivers and lakes. But groundwater contamination happens in darkness, spreading unseen until it appears in a well, by which time the pollution may extend for miles underground. The litany of groundwater contaminants reads like a chemical inventory of industrial civilization. Solvents from dry cleaners and degreasing operations, their molecules slipping through soil like toxic ghosts. Gasoline and diesel from leaking underground tanks, forming plumes that persist for decades. Agricultural chemicals, nitrates from fertilizer, pesticides designed to kill, herbicides that persist long after the weeds they targeted have gone, heavy metals from mining and industry, pharmaceuticals from septic systems and wastewater. Even the road salt that keeps winter highways safe eventually finds its way into groundwater, a creeping salinity that degrades water quality. Each contaminant behaves differently underground. Some, like nitrates, dissolve readily and flow with groundwater, spreading quickly but also potentially flushing out if the source is removed. Others, like chlorinated solvents, sink through aquifers like slow-motion waterfalls, pooling at the bottom in ways that make cleanup nearly impossible. Some attach to soil particles, creating a reservoir of contamination that slowly releases toxins for decades. Others transform underground, breaking down into compounds that may be more or less harmful than the original pollutant. The three-dimensional puzzle of contamination challenges our best engineering. A factory that leaked chemicals 50 years ago may have created a plume that now extends beneath hundreds of homes. The contamination doesn't respect property lines or political boundaries. It follows the physics of flow and chemistry, creating underground geographies of risk that map poorly onto our surface world of ownership and responsibility. Cleanup, remediation in the technical language, often seems like trying to unmix paint. Pump and treat systems pull contaminated water to the surface for treatment, but in heterogeneous aquifers, the pumping may miss pockets of contamination. Injection of chemicals to break down pollutants works in some cases, but risks creating new problems. Bioremediation, using bacteria to consume contaminants, shows promise, but requires patience measured in decades. Sometimes the only option is containment, trying to keep contamination from spreading while waiting for the slow processes of natural breakdown. But the fragility of groundwater extends beyond quantity and quality to the very architecture of aquifers themselves. In coastal areas, excessive pumping allows salt water to intrude into freshwater aquifers, a contamination that's nearly irreversible. The freshwater, being less dense, normally holds the seawater at bay, but drop the water table through overpumping and the sea moves inland underground, turning wells brackish, poisoning the aquifer with salt. Land subsidence tells another story of architectural fragility. When groundwater is pumped from certain types of sediments, the grains compact, the land surface drops, and the pore spaces that once held water collapse forever. Mexico City has sunk dozens of feet. Parts of California's Central Valley have dropped the height of a two-story building. This isn't just inconvenient, it breaks water pipes, damages roads and buildings, and permanently reduces the aquifer's ability to store water. It's like squeezing a sponge so hard it can never expand again. Climate change adds new uncertainty to old fragilities. Changing precipitation patterns may reduce recharge in some areas, increase it in others. More intense droughts stress aquifers as surface water supplies fail and groundwater pumping increases. More intense storms may overwhelm the soil's ability to absorb water, increasing runoff at the expense of recharge. Rising seas threaten coastal aquifers with saltwater intrusion. The hidden waters that buffered us against climate variability may themselves become casualties of climate change. Yet within this catalogue of fragility lies the seed of stewardship. Understanding vulnerability is the first step toward protection. Around the world, communities are awakening to the need for groundwater governance, for treating underground water with the same care we've learned to apply to rivers and lakes. Some solutions are technological. Managed aquifer recharge, deliberately directing water underground during wet periods, can help refill depleted aquifers. Stormwater that once rushed to the sea through concrete channels is being directed to infiltration basins, where it can percolate into aquifers. Treated wastewater, rather than being discharged to rivers, is being used to recharge groundwater, creating new supplies from old problems. Other solutions are regulatory. Well spacing requirements prevent too many straws from drinking from the same underground glass. Pumping allocations share limited resources. Protection zones around wells prevent activities that might contaminate groundwater. Some jurisdictions have gone further, recognizing groundwater rights for ecosystems, ensuring that enough water remains underground to support springs and groundwater-dependent streams. But perhaps the most important solutions are cultural, shifts in how we see and value groundwater. Indigenous peoples often speak of water as a relative, deserving respect and reciprocity rather than mere extraction. This perspective, which seems mystical to industrial mindsets, may be the practical wisdom we need. When we see groundwater as part of a living system, rather than an inert resource, stewardship becomes not just policy but ethics. Community-based groundwater management shows promise where top-down regulation fails. When neighbours share an aquifer and can see the consequences of overpumping in each other's failing wells, self-regulation often emerges. Traditional systems like the Subak irrigation communities of Bali have managed water sustainably for centuries through social cooperation rather than technological fixes. Modern versions are emerging as communities realise their shared dependence on hidden water. Monitoring becomes meditation when we pay attention to what it reveals. Each measurement of a dropping water table is a teaching about limits. Each detection of contamination is a lesson in connection. How what we do on the surface affects the depths. How the past reaches into the future through persistent chemicals. How individual actions aggregate into collective consequences. The fragility of groundwater is not a reason for despair, but a call for care. Yes, we've damaged many aquifers, some perhaps beyond recovery in any timescale that matters to human planning. But we've also learned, and we're learning still. We know now that groundwater is not an infinite resource, but a finite trust fund. We understand the connections between surface and depth, between present actions and future consequences. We have the tools, technical, regulatory, cultural, to do better. Stewardship of groundwater requires thinking in timescales that challenge quarterly reports and election cycles. It means considering the inheritance we leave, not just of money or property, but of water. It means recognizing that the water we pump today fell as rain when our great-grandparents were children, and the water falling as rain today might not reach the aquifer until our great-grandchildren are old. This is the profound shift groundwater asks of us. From extraction to relationship, from use to stewardship, from the illusion of isolation to the recognition of connection. Every well is a responsibility. Every spring is a trust. Every aquifer is a community resource that transcends property lines and generations. In protecting groundwater, we protect not just a resource, but a relationship with the earth, with each other, with a future that depends on our present choices. The fragility of groundwater is real, written in dropping water tables and spreading contamination plumes. But fragility acknowledged becomes strength potential. When we recognize what can be broken, we learn to handle with care. When we understand the patience of aquifers, we might learn patience ourselves. When we see the connections groundwater reveals, between rain and depth, between past and future, between human action and geological consequence, we might yet become the stewards these hidden waters require. Chapter 10. The Water Cycle. Revisited, we return now to the ground circulation, the planetary pulse that connects every drop of water to every other, that links the highest clouds to the deepest aquifers in an endless dance of transformation. But having journeyed through the underground, having seen the secret life of groundwater, we understand this cycle differently. It's not just the simple diagram from textbooks, arrows showing evaporation, precipitation, and runoff. It's a living system of incredible complexity, where water moves not just through space but through time, carrying stories and minerals, supporting life in forms both obvious and hidden. Begin again with the ocean, that vast reservoir holding 97% of Earth's water. But see it now not just as surface but as depth, not just as blue expanse but as the ultimate recipient of groundwater's gifts. Every spring that flows to a stream, every stream that flows to a river, every river that flows to the sea carries groundwater's contributions. Minerals dissolved from deep rocks, nutrients processed by underground organisms, the chemical signatures of water's underground journey. Where rivers meet the sea, fresh groundwater also arrives unseen. Submarine springs discharge directly into the ocean through the seafloor, sometimes with enough force to create boils on the surface, fresh water rising through salt water like inverse rain. Along every coastline, groundwater seeps through beach sand and underwater sediments, a hidden flow that may exceed the visible flow of rivers. The ocean receives these gifts, the patient accumulation of underground water finally returning to the source. From the ocean's surface, water rises as vapor, that invisible gas that makes Earth's atmosphere breathable and weather possible. But this isn't uniform ascension. Water molecules evaporate more readily when they're lighter, those containing ordinary hydrogen rather than its heavier isotope, deuterium. This atomic sorting begins the signature writing that will allow scientists to trace water's path. The vapor carries these ratios like a passport, recording conditions at its point of departure. Rising vapor eventually cools and condenses, but not randomly. It needs surfaces, particles of dust, salt, pollen, bacteria even, lifted high into the atmosphere. Each raindrop or snowflake begins around such a nucleus, water vapor finding its way back to liquid or solid form through the intermediary of these aerial particles. Some of these particles come from far away: Saharan dust fertilizing Amazon rainforests, Asian pollution affecting California precipitation. The water cycle is also a particle cycle, a chemistry cycle, connecting distant places through the atmosphere. When precipitation falls, the cycle appears to begin again, but we know better now. We've seen how a raindrop's fate depends on where it lands, how the same storm might send some water rushing across pavement to storm drains in the sea, while other drops landing on forest soil begin the slow journey into groundwater. We understand that the visible runoff, the stream swelling with storm flow, is only part of the story. The invisible infiltration, the patient percolation into soil and rock, may be the more important chapter. Think of soil differently now, not as mere dirt, but as the critical interface between the atmospheric and underground parts of the water cycle. In those first few feet of Earth, immense decisions are made. Root systems drink here, sending water back to the atmosphere through transpiration. Soil organisms process water, affecting its chemistry. Clay particles hold water in thin films, sometimes so tightly that plants can't extract it. The soil is water cycle's great mediator, determining what returns quickly to the atmosphere, what runs off to streams, what descends to become groundwater. The descent into groundwater transforms water from a participant in weather to a participant in geology. Underground, water moves through the rock cycle, as well as the water cycle. It dissolves minerals, creating the caves of limestone regions and the springs that discharge from them. It deposits minerals elsewhere, cementing sediments into stone, filling fractures with crystalline veins. Every aquifer is both a water reservoir and an active geological system, with groundwater as the agent of change. Time dilates underground. While surface water might complete multiple cycles, ocean to cloud to rain to river to ocean, in a single year, groundwater operates on different schedules. Water entering the Nubian sandstone aquifer beneath the Sahara might not emerge for 30,000 years. Water in shallow aquifers might take decades to centuries. This temporal stretching means the water cycle isn't a simple loop, but a complex spiral through time, with some water taking express routes and others the geological slow train. Springs mark the return of groundwater to the surface cycle, but what different water emerges? It has been filtered through miles of rock and soil, its turbidity settled out, its biology transformed. It carries minerals from deep sources, calcium making it hard, iron staining it red, sulfur giving it distinctive odours. It might be warmer or cooler than the air temperature, carrying thermal memories of its underground journey. Spring water is travelled water, experienced water, water that has stories to tell in its chemistry. Streams fed by groundwater behave differently than those dependent only on runoff. They flow through droughts when other streams fail. They run cooler in summer, warmer in winter, moderated by groundwater's thermal stability. They support different ecosystems, trout in groundwater-fed streams, specialized plants along spring runs. The contribution of groundwater to surface flow isn't just about quantity but quality, not just about water but about the conditions that water creates. Plants participate in the water cycle in ways we're still discovering. Yes, they transpire enormous amounts, A single large tree might send hundreds of gallons daily from soil to atmosphere. But they also direct water underground through their root systems, creating preferential flow paths that speed infiltration. When rain falls on a forest, some water never touches the ground, intercepted by leaves and evaporated directly back to the atmosphere. Other water flows down trunks, concentrated around root zones where it's more likely to infiltrate deeply. The atmosphere itself is an aquifer of sorts, holding water temporarily in vapour form. The amount is small compared to other reservoirs. If all atmospheric water vapour condensed at once, it would cover the Earth to a depth of only an inch. But this aerial aquifer turns over rapidly, completely recycling every 8 to 10 days. It's the water cycle's rapid transit system, moving water quickly compared to the patient pace of groundwater. Humans have inserted themselves into every part of the water cycle. We've created new pathways, aqueducts and pipelines moving water across watersheds, breaking natural basin boundaries. We've accelerated some processes, pumping groundwater that would have taken centuries to emerge naturally. We've created new reservoirs, from surface reservoirs that increase evaporation to deep injection wells that may permanently remove water from the active cycle. Cities dramatically alter the water cycle's local expression. Pavement prevents infiltration, sending water that would have recharged aquifers racing through storm sewers to streams. Buildings and roads create heat islands that affect local precipitation patterns. Deep foundations and underground structures redirect groundwater flow. Urban water use concentrates water from large areas, uses it briefly, then discharges it through treatment plants, creating artificial springs of treated wastewater. Agriculture is perhaps our largest intervention in the water cycle. Irrigation moves water from rivers and aquifers to fields, where much evaporates before reaching roots. This accelerated evaporation can change local weather patterns. Irrigated areas are often cooler and more humid than surrounding lands. In some places, so much groundwater is pumped for irrigation that the water table has dropped hundreds of feet, breaking the connection between groundwater and surface water that sustained streams for millennia. Climate change is rewriting the water cycle's patterns while we're still trying to read the original text. Warmer air holds more moisture, about 7% more for each degree Celsius of warming. This means more water vapour in the atmosphere, potentially more intense precipitation when conditions are right for rain. But it also means more intense evaporation, more severe droughts when rain doesn't come. The extremes expand while the middle ground shrinks. The water cycle responds to these changes in complex ways. More intense rainfall might seem good for groundwater recharge, but if it falls too fast for soils to absorb, it runs off instead of infiltrating. Warmer temperatures mean more precipitation falls as rain rather than snow in mountain regions, changing the timing of runoff and recharge. Melting permafrost releases water frozen for millennia, adding ancient water to the active cycle while potentially destabilizing northern landscapes. Yet the water cycle's fundamental resilience gives hope. Water is neither created nor destroyed in any process we control. It only changes form and location. The same molecules that dinosaurs drank still circulate. The water cycle has survived ice ages and hothouse periods, asteroid impacts and volcanic catastrophes. It will survive us, though in what form and favourability for human life remains to be determined by our choices. Understanding the water cycle through the lens of groundwater reveals its true complexity and beauty. It's not a simple circle, but a web of interconnections spanning orders of magnitude in time and space. It's not just physics, but biology, not just chemistry, but geology. Every drop of water is on a journey that might take it through clouds and streams in weeks, or through deep aquifers over millennia. Every molecule has stories of the cloud it condensed in, the soil it infiltrated through, the rock it dissolved, the life it supported. We end where we began, with water, but with deeper appreciation for its hidden journeys. The next time you see rain, think of its possible futures, rushing down gutters or slowly seeping into soil, joining streams or aquifers, returning to the atmosphere in days or centuries. The next time you drink from a spring or well, consider the journey that water has taken, When it fell as rain, what rocks it passed through, what darkness it knew before returning to light. The water cycle, revisited through Groundwater's patient perspective, teaches patience. It shows that quick and visible aren't always most important, that the hidden supports the seen, that timescales matter. It reveals that we're part of something much larger than ourselves, a planetary circulation system that connects every place to every other, every moment to deep time, every living thing to the water that moves through earth and sky in endless, patient, necessary circulation. Act 3, The Gentle Return. We have travelled far together, you and I, though we've moved more in depth than distance. From the rain's first touch upon the earth to its emergence centuries later from hidden springs, we've traced water's secret journey through the patient architecture of stone and time. We've discovered life in the darkness and human stories written in well and spring. We've learned to listen to the earth's liquid whispers and confronted both the fragility and resilience of the hidden waters. Now, as our journey together draws toward its close, let's remember what we've discovered. We've learned that beneath every landscape, beneath the place where you rest right now, water moves with the patience of centuries, not rushing like surface streams, but seeping, percolating, flowing with a slowness that challenges our hurried sense of time. This is groundwater, the Earth's memory made liquid, the planet's patience expressed in H2O. We've seen how water finds its way into the Earth through the generous spaces between sand grains, through the tiny pores in sandstone, through fractures in granite that map the Earth's ancient traumas. We've followed individual raindrops on journeys that might span human lifetimes, moving through darkness, picking up minerals and stories, transformed by their underground pilgrimage. We've discovered the architecture of aquifers, those natural libraries of stone and space, where water is held and shared according to laws older than any human code. From the vast sandstone formations beneath deserts to the honeycombed limestone through which underground rivers flow, each aquifer has its own personality, its own way of receiving, storing, and releasing water. We've tasted the age of water, learning that some groundwater is fossil, liquid memories of climates that vanished before human civilization began. This ancient water, protected in deep aquifers, connects us to deep time in ways that fossils and rocks cannot. To drink such water is to commune with the rain that fell on landscapes we can barely imagine. We've witnessed water's quiet emergence through springs, those magical places where the underground world offers its gifts to the surface. From the smallest seep supporting a patch of green in the desert to the great springs that birth rivers, we've seen how groundwater returns to the light, carrying with it the minerals, the temperatures, the chemical signatures of its underground journey. We've met the unexpected inhabitants of the dark waters, bacteria and other microorganisms that thrive without sunlight, transforming minerals, processing chemistry, living at speeds that make glaciers seem hasty. And in caves, we've encountered the pale, blind creatures that have adapted to life in perpetual darkness, reminding us that life finds ways to persist in the most unlikely places. We've traced the human thread, 10,000 years of finding, using, celebrating, and sometimes harming the waters beneath our feet. From the ancient Qanat builders to modern hydrogeologists, from sacred springs to contaminated aquifers, we've seen how human history is inseparable from groundwater history. We've learned to listen to the earth with tools both ancient and modern, reading the landscape's subtle clues, sending waves of sound and electricity through rock, tracing the chemistry of water's journey. Each method of listening has revealed new complexities, new connections, new reasons for both concern and hope. We've confronted the fragility of these hidden waters, the dropping water tables, the spreading contamination, the permanent loss of storage through land subsidence. But we've also discovered the seeds of stewardship, the growing understanding that groundwater is not an infinite resource but a finite trust requiring our care. And finally, we've seen how groundwater completes and complicates our understanding of the water cycle, adding the dimension of geological time to atmospheric cycling, connecting the quick waters of rain and river to the patient waters of aquifers. All of this returns us to the question I asked at the beginning: what are the softest places you've ever walked? Perhaps now that question resonates differently, for now you know that beneath those soft places, beneath the moss, the sand, the snow, the soil, water moves in darkness. The softness you felt was the Earth's way of showing you its porosity, its ability to receive and hold water, its participation in the vast, slow conversation between rain and rock. Every soft place is a door to the underground waters, every spring is a window into hidden flows, every well is a connection between the world of light and the world of darkness, and you, resting where you are part of this system. The water in your body has made these journeys from cloud to soil to aquifer to spring to river to sea to cloud again. You are the water cycle embodied, groundwater temporarily organized into human form. If this story has brought you some measure of peace, if it has helped your thoughts settle like sediment in still water, then it has served its purpose. And perhaps you might share this peace with others, not urgently, not insistently, but gently, like water sharing itself with soil. For the story of groundwater is ultimately a story about sharing, how water is shared between rain and earth, between darkness and light, between past and present, between all living things. Consider what lies beneath your feet, not just tonight but tomorrow as you walk through your day. Beneath the parking lot, beneath the forest trail, beneath your garden, water moves with its ancient patience. It carries no anxiety about reaching its destination. It holds no resentment about the darkness of its journey. It simply flows, seeps, percolates, according to forces larger than itself, participating in cycles older than mountains. There's a teaching in this patience. In a world that prizes speed and visibility, groundwater reminds us that the most essential movements are often the slowest and most hidden. The water that sustains the forest moves underground. The springs that have supported civilizations for millennia are fed by rain that fell when those civilizations were young. Patience is not just a virtue but a necessity, written into the very physics of how water moves through stone. As you drift towards sleep, or if sleep seems distant as you simply rest in the darkness, you might imagine yourself as groundwater. Feel yourself sinking slowly through layers of time, leaving the bright anxiety of the surface world, descending into the patient darkness where time moves differently. Let your thoughts percolate through the spaces in your mind, finding their own level, their own pace. And remember, even in the deepest aquifer, even in water that has been underground for thousands of years, the potential for emergence remains. Every drop of groundwater will eventually return to the surface, will rejoin the quick, bright world of rivers and rain. But it returns transformed by its journey, carrying gifts from the darkness, minerals for life, coolness for hot days, reliability through droughts. You too will emerge from this quiet time transformed in small ways. The stories of underground water will percolate through your dreams, perhaps, or simply rest in the aquifers of memory, ready to surface when needed. You'll carry with you the knowledge that beneath the solid-seeming world flows another world, liquid and patient, essential and hidden. Sleep well when sleep comes, and may your dreams flow gently as groundwater through sandstone, as springs emerging into starlight, as rain returning to the patient earth. May you rest in the knowledge that you are supported by systems vast and patient, by water cycles that have operated since the world began and will continue long after human worries have dissolved like minerals in the flow of time. And when you wake, refreshed by rest as the earth is refreshed by rain, perhaps you'll remember the secret rivers flowing beneath your feet, the ancient waters waiting in darkness, the springs that connect the hidden world to the one we know. Perhaps you'll move through your day with some of groundwater's patience, some of its persistence, some of its quiet certainty that every journey, however long, however dark, leads eventually back to the light. This has been our journey together through the hidden waters. Thank you for lending your attention to these quiet flows, for descending with me into the patient darkness, for caring about waters you cannot see but which sustain everything you can. The story of groundwater continues. in the rain falling now somewhere on Earth beginning its underground journey, in the springs flowing at this moment from hidden sources, in the wells drawing up water older than memory, in the patient percolation that connects all waters in endless necessary circulation. Sweet dreams and gentle flowing,